All right, so building on this first application of the transformation formula we came up with. So again, we just started with any pair of random variables, but we use this transformation, namely y1 is the transformation that adds the original two things together, and y2 is the thing that subtracts them from one another. We get this. We get that the new joint density for y1 and y2 as variables is given by this. Okay, so yeah, so let's actually see that with an application of this that the book does, which I think is pretty helpful, is the following. So example, suppose that x1 and x2 are both distributed as uniform 0, 1 random variables, okay, and they're independent. Well, if these things are independent, you know what their individual marginals are, right? So f sub x1 of little x1 is equal to what? Well, it's just 1 if 0 is less than x is less than 1, and 0 otherwise. And of course, that's also true, or sorry, x1 is less than less than 1. And the same is true for f sub x2 of x2. So this is just going to be 1 if x2 is between 0 and 1, and 0 otherwise. Okay. So what's the joint density? Well, it's just going to be the product of these two things. I would multiply these two things together. Okay. So, well, let me just kind of write that down just for good measure. Okay, so it's equal to fx1 of x1 times fx2 of little x2, which is just 1 if what? If 0 is less than x1, same thing for x2, and these are both less than 1. So x1 and x2 are both between 0 and 1, and it's 0 otherwise. And it's pretty easy to imagine that what we have here in three-dimensional space is we only have action for this density on the unit square down on the xy plane, with one vertex at the origin, one vertex at 1, 0, one vertex at 0, 1, and the other vertex at 1, 1. And everything is at height 1 above that. So that thing has volume 1 underneath it. Okay? But again, if we do this transformation, if we take y1 to be the sum, and we take y2 to be the difference, okay, then we know that that we get x1 is 1/2 y1 plus y2, and we get x2 is 1/2 y1 minus y2. Okay. And what is the new joint density of y1 and y2 in these new variables? Well, it's going to be half of the original density with x1 replaced by what it is in terms of y1 and y2. So it's going to be 1/2 y1 plus y2, comma 1/2 y1 minus y2. Okay, so this is the density for the joint density for these new variables. The first variable being the sum of x1 and x2, and the second variable being the difference. Okay? So what does that look like in practice? Okay, so, let me just kind of write this over here. So remember, x1 and x2 were distributed as uniform 0, 1s. Okay? And y1 is x1 plus x2, y2 is x1 minus x2. Okay, so f y1, y2, the joint density, little y1, little y2 is 1/2 times the density for x1 and x2 with variables replaced by those things. So what is that? Well, it's going to be 1/2. 1/2 times 1. Remember, in that, right, the density was equal to 1 if x1 and x2 were between 0 and 1. Okay, so let me just write that. So this would be 0 is less than, remember, what was x1? Okay, well, x1 is, again, 1/2 y1, or let me do capital Y1 plus capital Y2, and x2 is 1/2 capital Y1 minus Y2. Okay, so this was for 0 less than x1 less than 1, which means that I have 1/2, well, let me use lowercase letters now. Y1 plus Y2 less than 1, and also for 0 less than 1/2 Y1 minus Y2 less than 1, and 0 otherwise. So as we look at this, one question we may ask ourselves is, all right, so we have this joint density, and if all the theory is sound, then this thing ought to integrate to 1 over the region in question. So let's at least kind of take a peek at this to make sure that that's the case. So what I'm going to do is I'm going to rewrite this. I'll write it as, let's see, 1/2. And if I multiply the inequalities through by 2, this is like for 0 less than y1 plus y2 less than 2. Okay, and for 0 less than y1 minus y2 less than 2, and 0 otherwise. Okay, and the question is, what kind of a region are we dealing with here, right? So what is this region describing? What is up with this? Okay, and once we can determine that region, we can just think about the fact that, well, the height everywhere over that region is 1/2. Okay, and so whatever that region is, the area of that region times 1/2 had better be equal to 1. So let's think about what that region is, right? So what's this region? And it's kind of weird because we've converted over to different coordinates, y1 and y2. So I'm gonna draw some axes here, and one of these is the y1 axis. Okay, we'll call this the y1 axis, and this is the y2 axis. And what you do is you say, well, okay, what's the lower bound of this thing? Okay, so the lower bounding region for this first thing is basically y1 plus y2 equals 0. Y1 plus y2 equals 0, which is the same thing as y2 equals minus y1. Okay, so y2 equals minus y1, which is this. Okay, so this is, let me just say y1 plus y2 equals 0. Okay, and then if I go back over into here and I say, okay, well, what about the upper limit of this region? Well, that's y1 plus y2 equals 2, which is the same thing as y2 equals 2 minus y1. All right, so that's a parallel line like this. Okay, so this is y1 plus y2 equals 2. Where do these things intersect? Well, at 2 and at 2. Okay. And what region is it that, so y1 plus y2, that y1 plus y2 equals 0, y1 plus y2 equals 2. Where is y1 plus y2 between these two things? Well, okay, let's think about it. Just kind of plug in a value that you can see is clearly in here, like 1 comma 0. So y1 equal to 1 and y2 equal to 0 is clearly in between these two lines. And y1 plus y2 is equal to 1, which is between 1 and 2. So actually we're talking about this region between these two lines. But, just hang on here. We also have these other two, this other condition we have to be concerned with, okay? So we have this guy here and this guy here that we have to concern ourselves with. y1 minus y2 equals 0, and y1 minus y2 equals 2. Okay, so that's a couple of other lines that I'm going to draw in here. So y1 minus y2 equals 0. That's this. Okay, so this is, y1 minus y2 equals 0. That's the same thing as y2 equal y1. And then y1 minus y2 equals 2. That's the same thing as y2 equals y1 minus 2. Okay, so that's this line. Okay, so this is y1 minus y2 equals 2. Okay, and once again, you can kind of check that the region we're talking about here is between these two. Okay, but I want both of these things to be true at the same time, right? Which means I'm talking about this region, which means I'm talking about this region, right? Let's see, what color do I want to use here? I'll use purple. Okay, right here. Right, this is the region that we're talking about in the y1, y2 plane. Okay, and what is the area? What's the area of that thing? Well, I mean, check it out. This point right here, that point right there is on both of those upper lines, okay? And this point down here is on both of those lower lines. Okay, and what points are those? Well, the upper one, okay, so that's, basically the point 1, 1, correct? Because 1, 1 satisfies y1 plus y2 equal 2. 1 plus 1 is 2. But it also satisfies y1 minus y2 is 0, right? So this is the point 1, 1. And by the same token, this is the point 1 minus 1. Okay, and so if you think about this for a second, we can actually compute the area of these little triangles right here. Okay, and they're actually congruent triangles, okay? But each have a base length of 2 and a height of 1. Okay, each has a height of 1 and a base length of 2. Okay, have a base length of 2 and a height of 1 for each one of those. There's 2 of those triangles. Okay, so let me just say that the volume under this density equals the area of the purple region times the height of the density, which is 1/2. Okay, Well, what is the area of that purple region? So it's two triangles, so it's going to be 2 times, okay, and they both have the same area, those triangles. So it's 1/2 base length, which is 1 times height, right, so actually the base length is 2, I'm sorry, times the height, which is 1, okay, and then of course I have this remnant factor of 1/2 right here, and lo and behold, the 2's cancel and you end up with 1, which is exactly what you would expect, okay? So indeed, this is a density. We kind of knew it had to be, but I wanted to get a little bit of extra practice with working in multiple dimensions here. Okay, so that's kind of an interesting little way to end this exploration. But hopefully that was helpful. Just kind of seeing how transformations work, seeing how they can give rise to new densities. Okay, all right. I'll stop there and I will see you after Easter weekend.